how radar equipment works, the basic principles behind it, and the factors that affect the reliability and performance of radar equipment. Radar is an acronym for Radio Detection and Ranging, and the method employed is based on a simple fundamental principle. Short radio waves, or what are known as electromagnetic waves, are transmitted by radar and are reflected by objects that obstruct its path. The radar transmits a short burst or pulse of electromagnetic energy which hits an object, and some of that pulse returns down its original path back into the scanner. Since the velocity of propagation is known, it is the same speed as light, it's easy to calculate the distance to the object, as long as we are able to measure the time from which transmission is started until when the echo returns. The length of the transmitted pulse must be short in order to distinguish between echoes located close to each other. On board a ship, the radar has two main tasks. One is to detect other ships and provide an aid to prevent collisions, as radar can see in fog and darkness. The other is to assist in navigation, particularly at landfalls and when navigating close to land. The radar detects and provides the position of coastal objects, enabling the ship to plot its position. Radar transmissions are radio waves or electromagnetic waves similar to light, and consist of a series of crests and troughs. The radar transmits a short pulse of electromagnetic energy, which consists of crests and troughs. Transmitted electromagnetic waves are not all the same. They vary in their wavelength. The wavelength is the distance between two successive crests of waves. By international agreement, electromagnetic waves of a length between 0.1 to 30,000 millimeters are known as radio waves. Frequency is another way to measure a wave motion. Frequency indicates the number of crests which pass a fixed point per unit time. Because the speed of the electromagnetic wave is constant, the frequency and wavelength are always proportional. If the wavelength is long, i.e. the distance between the crests is long, comparatively few crests will pass the fixed point per second, and the frequency will be low. If, on the other hand, the wavelength is short, more crests will pass the fixed point per second, and the frequency will be higher. Most marine radars transmit in the X-band or the S-band, corresponding to approximately frequency of 9,000 and 5,000 megahertz respectively. Both types have advantages and disadvantages. A short wavelength is preferred in shipboard radar systems because there is a relationship between the size of the antenna, the wavelength, and the horizontal beam width of the transmitted pulse. The larger the horizontal width of the scanner, the smaller is the horizontal angular beam width when considering the same wavelength. This radar block diagram can be divided into 5 main parts. Scanner or antenna, which directs, transmits and receives the radar pulses. Transmitter unit with magnetron, which generates the appropriate radar pulse. Receiver and amplifier unit, which amplifies and processes the received pulses reflected back from remote objects. Display unit, which presents the information as a suitable picture. Modern sets have raster scan displays, which are similar to a television with daylight viewing, making their use far easier than older video display units. Power supply, which provides power to the various radar parts. It is not necessary for the radar operator to know the in-depth details of the radar components or how they interface. However, for safe and efficient use of the radar, a basic understanding of how radar works, its capabilities and limitations, is a minimum requirement for all navigators using radar in their work. Click on the buttons to learn more. Click on the buttons to learn about radar displays. Radar echoes are displayed on a display screen. This display screen is sometimes referred to as a planned position indicator, or PPI. The display screen may be an older cathode ray tube or a modern raster scan display. The modern screen allows it to be observed in normal daylight conditions and is used by most merchant ships. All screen types provide information of range and bearings of all targets in a way suitable for navigation. They also indicate movement by allowing previous positions of all the echoes to be retained for a short time as a trail to show the path of an echo across the screen over a period of time. Radar echoes from other ships are normally displayed on a screen as dots or spots, while land will be shown as merged spots, forming continuous lines on the screen. The spots will be at the correct bearing and range from the center of the trace, and can be used for navigational purposes. The point on the screen, which is referred to as the center of rotation of the trace of the screen, is the obvious focal point of the data, and can be easily distinguished. Cathode ray tube displays are often referred to as planned position indicators, and are liable to burn over a period of time if the gain is too high. Raster scan displays are much easier to use, and provide information in any background light. Long persistence tube. The trace is rotated round in unison with the rotation of the scanner, and echoes previously recorded are retained on the screen for several rotations of the trace as afterglow trails. Raster scan displays are normally rectangular screens, like a television, with dimensions in the ratio of 4:3. Consisting of, for example, 1,024 horizontal lines and 1,280 vertical lines or picture elements. The screen is painted with a fluorescent layer with a very short retentivity. The radar receives all echo information in Cartesian form, and this must be converted into X and Y coordinates before it can be presented on a raster scan display. Most radars today, even the small ones used on pleasure craft, are equipped with raster scan displays, either monochrome or colour. The advantage of the raster scan display is that it can be viewed in daylight without a visor, and the capacity for additional graphic information is almost unlimited compared with the PPI. Important definitions. Radar trace is the line which rotates around the display screen and is in synchronism with the rotating scanner. Radar pulse is the burst of energy sent out at one single transmission, or radar sweep, as it is sometimes called. A radar scan is one complete 360 degrees rotation of the antenna. During one scan, normally several thousand pulses are transmitted. Echo spot is the dot on the screen which is painted there by the receiver after receiving an echo from a remote object. The spot size is important, as later notes will explain. In modern radar systems, both sweep and scan correlation may be used to filter away unwanted noise. Read the manufacturer's manual and do not mix the terms sweep and scan if you wish to understand the filtering system. The pulse repetition frequency, or PRF, is defined as the number of pulses transmitted per second. The pulse length is the size of the transmitted burst of energy, and though the range scale in use will determine the available pulse lengths, which of these required can be selected from the pulse length control from the selection available. Long pulse means more power, therefore longer radar range, but less resolution in range. Short pulse means less power, weaker pulse and less radar range, but better resolution in range. Selection of pulse length may affect the radar range resolution. The PRF is related to the pulse length, as the longer the period of transmission, the lower the number of transmissions can be accomplished in the same period of time, unless the resting period is shortened. Click the buttons to learn about radar range. The radar minimum range depends mainly on the following parameters: antenna vertical beam width, which is normally over 60 degrees, selected pulse length, and the delay or inertia between transmission and when the receiver is open to receive, height of antenna associated with the vertical beam, and how quickly it reaches the surface. The radar minimum range is hardly ever a problem in practice when using the radar for traffic surveillance and navigation. The maximum radar range will vary with changing weather conditions. However, during standard atmospheric conditions, which are 1013 millibars air pressure, 0 altitude and an air temperature of 18 degrees Celsius, the following formula can be used. Where Rmax is radar horizon in nautical miles, H1 is antenna height in meters, and H2 is target height in meters. In practice, during normal weather conditions, navigators can expect the radar horizon to be approximately 10% further away than the optical horizon. The most important parameters affecting the maximum detection radar range are antenna height of own ship, height of target, size of target, target reflecting properties and area, shape of target, and weather conditions. Sometimes a target can be visible to the eye and not to the radar because of its size and reflective properties, but also the reverse may occur for the same reasons. The following technical parameters must also be taken into account: transmitted power and pulse length, wavelength of the signal, effectiveness and power loss in the antenna, general noise and interference figure, number of pulses transmitted per scan, loss of power in the waveguide during both transmission and reception, and finally display parameters and their effectiveness. Click on the buttons to learn about range discrimination. Range discrimination is the ability of the radar to discriminate between two small objects close together on the same bearing and display them as separate echoes on the display screen. The further object must not be in the shadow of the nearer one. The most important parameters affecting range discrimination are the selected pulse length and the size of the spot on the screen. If possible, short pulse and short range should be selected and gain carefully adjusted. This animation tries to illustrate what may happen when two ships are close in range and the radar is operated on short pulse. On the radar screen, two echoes can be seen, providing the object at the longest range is not in the radar shadow of the nearest one. This animation shows the same situation, but the radar is operated on long pulse. On the radar screen, only one echo is visible. The range resolution is the radar's ability to distinguish between two targets close to each other on same bearing. Click on the buttons to learn about bearing discrimination. Bearing discrimination is the ability of the radar to discriminate between two small objects close together at the same range but with slightly different bearings, and to produce them as two separate echoes on the radar screen. The bearing discrimination depends on the horizontal beam width of the transmitted pulse and the spot size on the screen. Correct gain setting will improve the bearing discrimination. This animation attempts to illustrate what may happen when two ships are close in bearing and X-band radar with a narrow horizontal beam width is used. Two echoes can be seen on the radar display, as long as the two ships are not hit within the same beam. The illustrated beam will unfortunately be larger than the real beam for purposes of this illustration. This animation tries to illustrate what may happen when the same beam hits two ships on the same range and slightly different bearings. Only one echo is displayed on the radar screen. The ships have merged together and are visible on the radar screen as one echo only. Bearing resolution is the radar's ability to discriminate between two objects located at the same range and only slightly different bearings. Click on the buttons to learn about bearing and range discrimination. The target's capacity to reflect radar pulses is dependent on the target's size, shape and material. When a radar pulse hits a target, some of the pulse will be absorbed and some of it reflected. How much of the reflected echo will return to the scanner is dependent on the shape and the angle of approach and the material of the target. Radar pulse reflection is subjected to the same laws as those for the reflection of light. The reflecting power of metal and water is higher than that of stone, wood and ice. If, for example, the detection range of a target of metal is 10 nautical miles, then the range of a target with the same size and shape but made of stone is approximately 6 nautical miles, of water 9 nautical miles, and ice or wood approximately 5 nautical miles. To improve the reflective properties of small ships and buoys, a special radar reflector can be used. The magnetic compass must have a safe distance from the radar because strong magnetic fields are generated in several parts of the radar. The exact safe distance is described in the radar manufacturer's installation manual, as well as in documentation provided by the classification societies. Normally, the safe distance varies between 1 and 5 meters. Although most ships today are equipped with a gyro compass, the magnetic compass is still the master compass on all ships, and every effort should be made to reduce any additional deviation. Marine radars transmit energy of varying strength in the form of short pulses or bursts. Pulsed power can produce biological changes not obtained with constant wave transmissions. At a close distance, transmissions from marine radars may pose a health hazard. Therefore, it is important to follow the instructions from the radar manufacturer closely and not take any chances. When working close to a radar antenna, make sure that the fuses are removed from the scanner motor or the total radar system, and a warning sign placed on the radar console clearly stating that no startup should be attempted before the work on the antenna is completed and there are no persons in the vicinity. The weather and the sea conditions will affect the visible scene from the wheelhouse windows and will also affect the radar display, with possible reduced detection and considerable unwanted echoes or clutter from the sea and rain. Those who have operated radar for some time will realize that sea and poor weather may reduce the effectiveness of the radar picture. These disturbances can be quite serious, but are usually easily detected. The operation of auto-clutter and interference controls is important to understand, and more details about this subject are given later. The effects of meteorological conditions will be found in the radar handbooks and manuals. Buttons to learn about transmission of radar waves. With normal meteorological conditions, the transmission of radar waves creates a radar range approximately 10 to 15% greater than the distance to the optical horizon. On average, one can say that normal conditions exist in areas with cold air masses. Generally speaking, the longer the wavelength, the greater is the tendency to bend around the curvature of the Earth and extend the radar horizon. Hence, you can expect the 10 centimeter radar to have a greater maximum range than the 3 centimeter radar. Whenever the air humidity is abnormally high, which it may be in fog, rain, snow and hail, a reduction in radar detection range can be expected. When warm, moist air exists over cold water, and the air is cooled from below, often giving rise to fog, the temperature and humidity will increase with altitude, and the radar wave will bend upward, decreasing the radar range. This is called subrefraction, and it decreases the radar range. When the meteorological conditions are favorable, say a calm day with warm, dry air over a surface layer of cold, moist air, the reverse of subrefraction may occur, and the radar pulse may follow the Earth's surface further, increasing the maximum radar range, creating what is known as superrefraction. With conditions of light wind and low clouds over cold water, we often get a condition called ducting, where the radar pulse and other radio waves are trapped within this duct. That is, the radar beam is reflected several times between the top of the duct and the sea surface, and the radar range can be increased considerably. Ducting can be expected to take place when a temperature inversion exists, and the atmosphere is calm. With conditions of considerable low ground fog, we may get a total radar blackout. This is extremely unusual, and normally the radar will provide data, though perhaps not as effectively as on other occasions. The reason for this is that all radar waves are reflected from the top of the fog and cannot penetrate through the fog down to sea level. Favourable conditions for radar blackouts are present when stationary warm air masses are located on top of cold sea. If the height of the fog is less than the height of the radar antenna, a total reflection of the radar signal from the top of the fog may take place. Sea clutter echoes are caused by reflection of the radar pulse from the sea waves. The reflection is specular, and conditions for the pulse to return to the scanner are favourable near the ship. At longer ranges, the beam will be reflected away from the ship and not produce any echo that can be received by the scanner, hence no sea clutter appearing on the screen. Marine radars are often equipped with automatic rejection systems to minimize the effect of sea clutter. This control is normally called anti-clutter sea control, and though it can be very useful, it can be dangerous and may not always have the correct setting and therefore should be used with great care, Otherwise, wanted small echoes may also be removed from the screen. If the radar is operated on manual C-clutter control, it is very important that there are some C returns remaining on the screen. Otherwise, the control could be too far adjusted. And once again, some wanted small echoes could also be removed from the screen. The higher scanner may often have more severe C-clutter visible on the screen than a lower scanner. This is because of the angle the radar pulse strikes the C surface and is able to be reflected back into the scanner. Rain squalls and showers appear on the screen as a mass of echoes, often merging into a solid area of returns. An intense rainstorm can be detected at a distance up to 25 nautical miles or more. Thunderstorms give excellent echoes, but even drizzle affects the radar visibility and may produce light diffuse echoes. The density of the water droplets makes a significant difference to the quantity of radar returns. Echoes of ships or land inside the rainstorm will be obscured by rain and clutter, and returns from targets beyond the rain area will lose some or almost all of their echo strengths. Use short pulse to distinguish targets inside the rain area, and long pulse to detect targets beyond the rain. A marine radar has manual and automatic anti-rain clutter controls, which remove part or all of these echoes from the screen. As with sea clutter, they should be used very carefully, as they can remove echoes of targets which are needed for safe navigation. Some radars have autocorrelation controls, which deal with these returns and other interference, but once again should be used with care. During weather conditions, including heavy rain, thunderstorms and so on, the S-band radar is a better choice than the X-band radar, as it is less affected by small water droplets, and therefore there are far less echoes produced. The two pictures clearly show the difference between the S-band and X-band radar during heavy rain, as displayed on a Raytheon radar with a conventional PPI display. Some navigation marks are equipped with a transmitter and receiver, which detect the radar pulse from a nearby ship and transmit an identify signal. This is known as a Raycon. This signal is received by the ship's radar, which displays it as a line on the screen emanating from the position of the mark toward the screen edge. The Raycon normally transmits through the frequencies band, and therefore its signal is only received when the frequency matches that of the ship's radar. Often, a 10-centimeter radar will not detect any signal if it is transmitted only on 3-centimeter wavelength, or vice versa. Radar interference may also occur when own ship's antenna receives signals from another radar. These disturbances often take the form of fan-shaped broken lines emanating from the center of the screen. Most radar equipment contains radar interference rejection circuits to eliminate this disturbance. Others may also have correlation controls, which serve a similar purpose. Please note that when interference rejection or correlation controls are switched on, it will remove identity returns from Raycons which may confuse the navigator, who is looking for this to identify a navigational mark. Unfortunately, when a ship approaches and passes under an overhead power cable, the radar pulse may only be reflected back to the scanner, where it strikes the cable at right angles. This means it will appear on the screen as a single dot, and not as a line. The direction of the dot may gradually move according to where the perpendicular point of contact is occurring, and the range of the single dot is the slant distance to the cable from the ship, which may slightly differ from the chart and add to the confusion. Blind sectors are caused when the antenna is placed in a position where an object on the ship, such as a funnel, blocks out the radar view of the horizon on that bearing. All structures above or higher than the antenna will create blind sectors on the radar screen. Objects within these sectors will normally not receive or return radar pulses, and therefore be invisible on the screen. All navigators should be familiar with where the radar blind sectors are on their ship. It is relatively easy to plot the blind sectors if this is done during a period with a lot of sea clutter. The blind sectors can be seen as distinctly dark sectors in the sea clutter area, as no echoes from the sea will be returned in that area. Plot each sector on a plotting sheet and place this so it can easily be seen from the radar observer's position. The radar signal may be reflected from an object or obstruction on board own ship in such a way that the pulse reflects off the obstruction and then hits a target, and an echo returns down the same path. A false echo would then be painted on the screen at almost the same distance as to the real target, but on the bearing of the obstruction. This is known as a reflected echo. This false echo will often, but not always, be located in own ship's blind sector. The navigator should know exactly where own ship's blind sectors are located. This is important in order to take actions to minimize the effect of the blind sectors and avoid targets approaching in this sector without detection. Multiple echoes can be created by reflection back and forth between own ship and an object, and on each occasion sending some of the pulses back to the scanner before it finally receives the last echo. On the screen, there will be a line of echoes on the same bearing, and with equal distance between them. The true echo is the one closest to own ship. The shapes of multiple echoes are less defined than that of the original echo, and they weaken in intensity outwards. Reduction of gain and increase in the clutter will sometimes remove this type of false echo before the actual true echo disappears. Side lobe echoes are caused by the side lobes of energy, which are the unwanted lobes of transmitted energy radiated by the scanner in a different direction to that of the much stronger main lobe. Objects close to own ship may be picked up by the side lobes as well as by the main lobe. The effect of side echoes will only be observed at short ranges. Side lobe echoes appear as concentric arcs round the centre of the screen. Reducing gain carefully or increasing anti-sea clutter control will normally remove the less powerful side echoes. It is impossible to design a scanner without side lobes. However, modern slotted waveguide scanners are very efficient and have minimal side lobe transmissions. There may be several reasons why the heading marker line on the screen is aligned incorrectly. The correct gyro heading has not been fed into the radar. The gyro repeater in the radar is malfunctioning and not following the main gyro. The ship's fore and aft line is not in the same direction as the heading marker. The first two give incorrect true bearings, but correct bearings relative to the heading marker or relative bearings. When the heading marker on the radar screen does not exactly coincide with the ship's fore and aft line, or in other words, when the echo from a target straight ahead does not lie exactly on the heading line, then we have a heading marker error, where both true bearings and relative bearings are incorrect. Heading marker errors may have serious effects on the radar picture and have been the cause of many collisions. All of these errors can be dangerous and should be checked regularly. The third error above, due to incorrect position of the heading marker line on the screen, is a constant and is normally set by the installation engineer. It can be adjusted, and this discrepancy removed by reading the radar manufacturer's handbook and carefully following the instructions. As we have seen, the radar waves transmit in a straight line. A radar coastline echo appearance will be determined by the topography and the reflective properties of the coastline. The same applies to the reflection of echoes from all objects. Their radar echo appearance is determined by their shape and reflective properties. The radar picture can be quite different from the chart. For example, The radar picture at low tide will be very different from that at high tide if there is large difference between high and low water. Knowledge of the topography effect on the radar picture can be of great importance whenever own ship's position determination must be based only on information from the radar display. Also, similar to the visual scene, the radar view may be obstructed by other targets and land, which will make the displayed scene quite different to the charted one. Another important reason for the difference between the sea chart and the radar image is the radar range and bearing discrimination parameters. That is, how much the radar magnifies the echo in range and bearing. There are two main ways to measure the range of a target on the screen, either fixed range rings or variable range marker. VRM is the usual abbreviation for the variable range marker. The fixed rings are always more accurate than the variable range marker, but an object in a position between the rings must have the range interpolated, and therefore the VRM is always easier to use. The range ring should be placed at the inner edge of the spot for an accurate range, and the figure read off the remote indicator display. Regularly check the VRM against the fixed rings to ensure that it is still accurate. The normal way of taking a bearing is by the use of the bearing line and reading the actual bearing numbers off the remote indicator. This will normally be true bearing, providing the correct compass heading has been fed into the radar. Always place the bearing line through the center of the spot on the screen. When using the bearing figures round the perimeter of the screen, they should always be used with great care, as they will only be correct if they are concentric round the center of rotation of the trace. Regularly check the bearing marker accuracy by placing it over the heading marker and ensuring it reads the same figure. A quick continuous method of determining that the ship is maintaining the desired course is by the use of parallel index lines. The display can generate lines which can be positioned parallel to the heading marker with a fixed distance off when abeam. This distance is known as the cross-index range. This is a very useful and important method of determining safe navigation of the ship when navigating close to land or restricted water.